Awesome. All right, hi everyone. We have a new guest speaker today. So today we have Lasse Peters. He's a PhD candidate in the Department of Cognitive Robotics at Delft University of Technology. He's advised by Javier Alonso Mora and Laura Ferranti. His research interests lie in combining methods from game theory, optimal control, reinforcement learning, all towards an effort to design safe and efficient strategies for multi-agent interaction. So super relevant to all the stuff we've been talking about so far. Before he came to Delft, he was a full-time research scholar in the photogrammetry and robotics lab of Cyril Stachnis, and a visiting research scholar at UC Berkeley and hybrid systems lab with Claire Tomlin. That's actually the first place where I met Lasse. I was a PhD student there. And today we're going to hear about game-theoretic models of multi-agent interaction. So Lasse, go ahead and take it away.
Nice. Thanks for the kind introduction. So yeah, today's talk is on game-theoretic models for multi-agent interaction, so fitting this series of this lecture. And to give you an example of the kind of interactions that we are interested in this talk, I gave you a very common example of a multi-agent interaction that we have a lot here in the Netherlands, which is you trying to drive through Amsterdam or any other busy city during rush hour. And these multi-agent interactions, they are typically characterized by these scenarios where each player wants to achieve their own objective. For example, they may want to reach a certain goal position, and they also want to minimize their own control effort, but at the same time, they also need to sort of collaborate to some extent with other players, for example, in order to avoid collision. And here's a more structured version of a similar interaction. So here we have a car trying to navigate an intersection, and there's a bunch of other humans around or other agents. And what's also very clear in this setting is that the actions of each player are tightly coupled with everyone else. So typically we cannot predict what one player does without knowing what the others do, because there's a tight, strong interdependence of these actions. And as a last example, here's a bit more of an extreme example where we have similar patterns, where this human wanted to very urgently reach their goal. And they're kind of also forcing some collision avoidance behavior on the ego vehicle. So like we have these similar settings where each player minimizes their own cost in a certain sense. And that's exactly the perspective that we're taking in the framework of dynamic game theory. Before I continue here, is this banner covering the screen, or can you see everything?
We can see everything.
Okay, nice. So yeah, we will use this last example as a running example through the entire talk. And on the right, you can see like a toy version of this game, where we have only two players, the human and the robot. And we model this, when we try to model this problem as a game, we set up a coupled optimization problem. So we get one optimization problem for each player. So in the player ith optimization problem, where I is the index of the player, here the human or the robot, they minimize their own strategy, which in the simplest case is simply a sequence of control inputs. And they choose that strategy in order to minimize their own cost. So player I has their own cost ji, which in general may depend on their own trajectory tau I, or their own strategy, and the strategy of everyone else, tau not I. So we will use this not I notation to denote other players' quantities. And then in particular in robotics, we are also interested in capturing constraints. And so here calligraphic K, I are the constraints for player I, which in general may depend may also depend on the strategies of everyone else. For example, in order to model collision avoidance, but also dynamic feasibility or requirements of like staying on the road and aspects like that. Okay. And so before we kind of discuss what it means to solve such a game, let's quickly take a step back and do a quick taxonomy. So throughout this entire talk, we will be looking at discrete time systems. So the trajectory or strategy tau here for each player is a finite dimensional vector, which consists of control inputs at every time steps. Those control inputs are from the continuous domain, but the system is assumed to be evolving in discrete time. And we may get such a discrete time approximation from an otherwise continuous system, for example, from a direct transcription of the optimization problem. And then also, if we look at the cost, to contrast this a little bit with some of the game theory that you've already seen in this lecture, or in earlier lectures of this class, here we're interested in general sum cost structures, meaning that there's no particular structure to the cost relative between different players. So you've previously seen settings where there's a zero-sum game where the costs for player I are exactly the costs of minus the cost of player not I. But here, and for general interaction problems in robotics, we're typically interested in games that are not strictly adversarial, and they're also not fully collaborative. There's something in between. We have some aspects where players may compete. For example, each player wants to minimize their own control effort, but then there are certain aspects in which they collaborate. For example, they may all want to avoid collisions. And for the first part of this talk, we will also focus on open loop information structure, which means that tau I, so the strategy of each player is an open loop strategy, which is exactly encoded by this assumption that it's just a sequence of control inputs. And so, this open loop strategy basically just depends on the initial state, and we'll see how we kind of deal with that in a bit. So that's the setup. Now let's talk about what it means to solve a game. In order to get there, we first need to define what is called the best response set, which we define here as calligraphic S, or calligraphic SI for player I. And that set is a function of the opponent's strategy. So if we fix everyone else's trajectory, tau not I, then we can, calligraphic SI includes all the trajectories that minimize player I's cost while fixing the opponent's strategies. So from the perspective of the robot, let me move this out of the way here. From the perspective of the robot, this then means if, for example, we just choose the human to go slowly towards the right, then maybe the best response for the robot would be to slow down and pass the human on the left. Or if the human goes towards the robot, then it would have to brake quite aggressively and maybe pass it on the right. And so you can see how this best response of the robot is a function of the human's trajectory or strategy. And similarly for the human, if the robot goes to the right, then for the human, the best thing may be to sort of evade to the top and then still go to the right to reach their goal. But if the robot passes the human on the left, the human may hurry up a bit because they notice that the car is trying to pass them behind, right? But they will otherwise make progress towards their goal. And this is exactly the best response dynamics that I'm trying to convey here. And if we understand what it means to have, or how these best response dynamics work, we can now talk about what a generalized Nash equilibrium is. And especially the definition here is that a generalized Nash equilibrium is exactly a profile of strategies such that each of the individual players' strategies is a best response to the other players' strategies, which is a bit difficult to think about. So let's break this apart. So first of all, an equilibrium like that may look like the one on the right. So for example, the human may go toward what's their goal, and they may sort of try to speed up a bit for the robot to be able to pass them on the left, because also the human doesn't want to collide, right? So they both share collision avoidance responsibility. And so compactly, we will write this as a, usually we can compactly write this as just this compact notation where we say tau I star is in the best response set of tau not I star. And so intuitively, this means that no player has a unilateral incentive to deviate. So on the right, I've plotted the cost first for the robot at this equilibrium. And you can see that any other feasible choice of the strategy for the robot will always at least increase, not decrease the cost, right? So on the right, we have we've seen an increase of the cost. And if the robot was to choose a little bit the strategy to the left, they will also see an increase of the cost. So fixing the opponent's, the human's strategy at tau H star, the best thing that the robot can do is to play tau r star. And similarly, for the robot, we can also look at this. So we can, let me move this out of the way. For the robot, we can do the same thing. For the human, we can do the same thing. We can ask, okay, fixing the robot strategy, we also require that any other strategy has a higher cost for the human, right? And so if these conditions hold unilaterally for each player, then we found a generalized Nash equilibrium of this game. Now, this, of course, feels a bit centralized in the sense that we are solving this game for all of the players, and you may ask yourself, okay, how do we then actually apply this for decision-making on a robot where we don't control the human, right? And that is done by wrapping this in the framework of model predictive gameplay, or MPGP for short. And that closely follows the idea of model predictive control in the single player case. What we will do is that at every time step, the robot formulates a game of from the current initial state that they observe. And then they solve this game, so to say, in their head to find a generalized Nash equilibrium. And so that gives them two trajectories in this case. One for the human, which serves as a game-theoretic prediction of their behavior. And then also a plan for themselves, which is the corresponding best response. But importantly, both of these are computed jointly in a tightly coupled fashion. And that's exactly the strength of games, that they're effectively a tool for simultaneous prediction and planning in this framework. And so this model predictive gameplay idea is then that we do this at every time step, and we only ever apply the first portion of the plan. There's a question?
Yeah, so I guess in order to actually do this, you need to know the cost function of the human. But
Yes.
How do you get that?
That's a very good question. We will get to that in the last third of this talk, and there's also going to be a guest lecture by David Friedrich-Keil in week 9. But yeah, that's a very good observation. For now, the assumption is that we have the cost. Okay. So assuming we have the cost, we can use this for decision making, right? And so in this model predictive gameplay setting, each player or the robot will then apply their own portion of the strategy at every time step, but only the sort of the first segment, and they will replan in a receding horizon fashion. And this replanning is then done to also account for modeling errors. For example, if we don't have the exact cost description for other players, right? Or we have sort of some estimation errors in the states. Now that's the high-level idea. So in order to make this actionable, we need, of course, to understand how we actually solve these games. And that's what this second chapter is about. And we'll, for now, just focus on open loop trajectory games. So exactly those games that we've seen earlier, where the decision variables of each player in their optimization problem is an open loop sequence of control inputs. And as a first algorithm, I would like to go over the algorithm that is called iterated best response. So to understand how that works, let's quickly review the challenges of solving games. So the challenge is that the trajectory of each player, the equilibrium trajectory of each player depends on the equilibrium trajectory of everyone else, right? So we have this kind of chicken and egg problem almost. That's both the power and the challenge of games. It's the reason why they are capable, or why they have this able to model this tight coupling, but it also makes it difficult to find solutions. And so the key idea of iterated best response is that we will start with an initial guess of a trajectory profile, where the subscript here is just denotes the iteration, and then we will improve this guess, or we will update this strategy guess iteratively by exercising the equilibrium conditions as an update rule. What do I mean by that? So in the beginning, we have some initial strategy guess tau hat, and say we first want to fix the robot strategy and update the human strategy. So then we fix the robot strategy at this initial guess. And then we look at the cost of the robot, of the human, as a function of that trajectory while fixing the robot's trajectory, right? And so maybe the cost is like this, where like we're not at the minimum yet. And from the perspective of this optimization, tau r is a constant. And so we will now update the human strategy to be at that minimizer. And we get a new strategy iterate for the human. And then now it's the robot's turn. Now we fix the human's strategy and we plot the robot's cost as a function of their trajectory while fixing the human's trajectory. And we can again perform a unilateral minimization. And maybe now the robot decides, okay, if the human proceeds to the right, then I can kind of pass them on the left. Now we'll fix the robot strategy again and update the human. So importantly, whenever a player's strategy changes, the cost landscape of the other players may change again, right? So there's a reason that we have to re-optimize, and we continue this entire iteration until convergence, which means until this unilateral best response optimization no longer changes the strategy. And then clearly by construction, we have found an open loop Nash equilibrium in the sense that these unilateral optimizations, they will only stop optimizing if there's no unilateral improvement that any player can make. That's exactly the definition of a Nash equilibrium, right? So conceptually, this is a really nice idea, and it's a good thing to kind of keep in your head of when you think about Nash equilibria. And it has a few advantages. So first of all, it's easy to implement. You can implement it directly with standard optimization tools that you may already know from other contexts. And if it converges, it indeed finds a Nash equilibrium. However, the problem is in practice that it has no convergence guarantees. That you may often run into situations where it cycles. So where one player chooses one trajectory and then the other player changes their mind, and this never really converges to a fixed point. And also this is, for that reason, is slow to converge, and also each iteration is very expensive. So each iteration here is the solution of an entire trajectory optimization problem, right? So in practice, this is not a very good algorithm to use, especially not for online decision-making when these decisions are timely. So in practice, I would really recommend this just as a debugging tool. The reason why I'm including this in the slides is that it's a really powerful tool for you to debug your own game solvers. If you write a game solver and you want to check if the output of the game solver is indeed a Nash equilibrium, you can run unilateral optimizations at each player's strategy, and you can check if that solver would deviate from that strategy, right? And if it does, then clearly you have still a bug in your solver. And also, if you think about what kind of equilibrium behavior you expect, this is a good algorithm to kind of run in your head to verify whether a certain profile of trajectories can be an equilibrium. Okay. So then the question is, can we do better? And in particular, can we find an algorithm, or can we design it so that we don't have to, that we get better convergence properties and that we don't have to take these expensive single player optimization steps? And the main approach that I would recommend is what's summarized in the next few slides, which is by solving open loop games as a mixed complementarity problem, where the key idea is that rather than solving single player optimizations, we will directly search for a trajectory profile for all the players, so one trajectory for each player that satisfies the coupled KKT conditions of this coupled optimization problem that makes up the game. So if we look at the optimization problem for player I wants to minimize their own cost subject to some constraints. And the key requirement that we will add here is that we can express these constraints with a potentially non-linear algebraic representation H, where now the constraints is satisfied whenever H evaluated at tau I and tau not I is greater or equal to 0. And then taking this view, we can introduce the Lagrangian for this optimization problem of player I, which is simply the cost minus lambda transpose times constraints, where lambda is the dual variables that we've introduced. So it has the same dimension as the vector valued constraint h. And so with this Lagrangian, we can now formulate the coupled KKT system of this open loop generalized Nash game. So the coupled KKT system is as follows. For every player, we get these following equations that you probably already know from single player trajectory optimization. We have stationarity of the Lagrangian, of the gradient of the Lagrangian. So gradient of the Lagrangian for player I with respect to its own decision variables must be 0. Then we have primal feasibility, meaning that whenever, h I needs to be positive, or non-negative. And then we have dual feasibility. The constraint multipliers must be non-negative. And then also these two conditions are orthogonal in a sense. That means that whenever h is positive at a certain element, the corresponding lambda must be 0 and vice versa. So none of the two can be, not two of them can be non-zero at the same time. And in this coupled setting where we have now n players competing against each other, we simply stack all of these conditions for the n players. Now, the reason, the bridge that we can make here to mixed complementarity problems is that we can recognize this KKT system exactly as a mixed complementarity problem, which I will abbreviate as MCP in these slides, and is often done so in the literature, and that's different from MPC. So that's an important clarification here. So MCP stands for mixed complementarity problem, and because I assume that you don't know that framework, I will quickly give you an overview of its general form. So in general, in a mixed complementarity problem, we are given a function f mapping from Rd to Rd, then a vector of lower bounds L and upper bounds U in the same space, so also in Rd, and then we are tasked to find Z in Rd so that f evaluated at Z complements Z between the bounds. And that's just very compact notation for the following requirement. For each output of f, we want that one of the three conditions holds. So the J here is the index of the output. So J is running from 1 to D. We either require that if Z is at the lower bound, we require that f of Z for that element is greater or equal to 0. If Z is between the bounds, then we require f to be at the root. And whenever Z is at the upper bound, we require f to be smaller or equal to 0. Now, this, so you effectively can see this as kind of advanced root finding in a sense, because whenever Z is between the bounds, we exactly ask for a root. And whenever Z is at the upper or lower bound, we allow f to deviate to either side. And it seems like a weird problem that you maybe don't understand why you should care about it. But if you stare at this forward more, you can see that the KKT system exactly takes this form if we set up the problem data as shown below. I will not go through all of the setup here in the interest of time, but you are invited to verify that offline. So basically, Z is here comprised of both the primals and the duals of the original optimization problem, and then F includes the gradient of the Lagrangian and the constraints, and then we have some blocks for so L and U are blockwise -infinity, +infinity, or 0. To just give you an example of one of the conditions that we've encoded here, recall that in the KKT conditions, we had the stationarity of the Lagrangian, which required that the gradient of the Lagrangian with respect to the player's primal decision variables must be 0. And that's, for example, encoded by this top block here. We have set the lower and the upper bounds to ±infinity, which means that we are always in the case where Z is between the bounds. And so we are effectively enforcing for these elements of F that the gradient must be 0. And similarly, you can verify for all the other elements of the coupled KKT system that they're also implicitly encoded by this mixed complementarity problem. And so why are we going through this entire process of converting it? So solving MCPs is still hard, but turns out that when the gradient of F, which involves the second derivatives of the Lagrangian, is smooth and sparse, as it often is in robotic applications that we care about, then modern MCP solvers, such as Path, which is a very advanced and fairly old solver, or a fairly mature solver can find solutions very rapidly to these problems. So to give you an example, in like a 5-player game with 25 time steps, and we get a mixed complementarity problem with 3,000 decision variables roughly, which includes both primals and duals. And we can solve this problem within about 35 milliseconds. That, of course, the runtime will vary according to the hardness of the task, but this is kind of the rough ballpark. So you can totally use this for online planning. So that's, and yeah, as we should also see later for in the last chapter, this is a fairly flexible framework, because so long as you can write down the KKT systems for your game, you can easily convert it into this MCP format, hand it to Path, and get a solution quite quickly. Now that concludes the chapter on open loop games. Next, I would like to extend beyond these open loop games, but first, are there any questions?
Maybe I have a question about kind of like I guess like maybe what is the comparison, I guess you would describe MCP to? Because it seems like I guess maybe everything that can be specified with KKT can be reframed in your way. But in a sense, maybe like why is MCP uniquely good in robotics problems, like, and other solvers aren't? Like, I guess it's because of this sparse and smooth thing, but I don't know, like, what are kind of the other things people have done, and like what, like, you have a sense of why they just don't work here, they're just slower.
So my take on this, so there is a lot of specialized solvers. For example, there's AL games, and that we'll also discuss another solver that can be applied to open loop games. But I have yet to find a solver that's faster in practice than MCP, than Path in particular, right? So it's just that this Path solver for MCPs is very mature, and I'm including this in the slides because I think it's an underappreciated solver that's not used too much in robotics, but I think I often find Path even to be faster than like specialized QP solvers on QPs. So it's a very flexible tool to know about. Like it easily beats OSQP, which I found surprising the first time I saw it. So I think it's a useful tool to know about. There's room, so there's some specialized solvers, for example, from Borelli's lab on like SQP type methods for games. But given that Steven Dirkse and co-authors have engineered Path for a really long time, since the 90s, it's kind of difficult to beat it in terms of robustness and practice. So unless you have very special needs, and those needs may include, for example, the special information structures that we will discuss in this chapter, I would usually recommend for these open loop games to actually use Path. And also, I will have a link at the end. We have some nice libraries now to synthesize these MCPs directly from game description, so you don't even have to think about this conversion yourself. Does that make sense?
Yeah, that makes sense. Thanks.
Okay. Yes.
I'm not sure if I'm fully understanding. So when we formulate this interaction problem as a game, that's, I guess, solved in the robot's head, as you say, and we use the equilibrium strategy of the other player as a, I guess, a sense as a prediction. This is like essentially a unimodal prediction, right?
Yes.
Okay.
Yes. We will, that's also a very good question. We will, in the last part of this talk, relax that assumption and make multimodal predictions of players. As precisely because in practice we may not exactly know the intent, which will then manifest in there being sort of multimodal uncertainty about what they may do in the future. Okay. So then for the next chapter of this talk, I would like to extend beyond these open loop information structures and talk about feedback games. Now, first, why should you even care about feedback? So open loop games are powerful and they capture rich behavior. Even though open loop may sound scary, we can capture stuff like collision avoidance and other aspects of competition, and also the receding horizon replanning takes care of prediction errors for us, right? But an inherent limitation of this open loop formulation in which players choose control sequences is that they cannot capture certain aspects of indirect interaction. And to clarify what I mean by that, let's revisit our example. So in this example, say that the cost was for the robot to reach their goal while avoiding collision, and for the human as well, right? And so if we solve the game under open loop information structure with these costs, then we got these equilibria. This is just copied from the previous slide, right? But now say we added a cost term for the robot that required them to also minimize the human's control effort. In this setting, that's a little bit contrived, but it's easy to see that in some tasks where like we may be having some shared assembly task or whatever, we may actually do care about this. But in this setting, it's also not too difficult to reason about this, right? We may want to not get too close to the human so that they don't have to hurry so much. However, if we do this in open loop information structure, if we look at what happens to the cost, this is a cost that only depends on the opponent's decision variable. But the opponent's decision variable from the perspective of the robot is a constant, right? And so if we add this cost, all that happens is that fixing the opponent's decision variable, our entire cost landscape gets lifted. That doesn't change the position of the minimizer. So if we were now to verify, is this a Nash by just running one round of iterated best response, we would notice that we are still at the Nash equilibrium. And so we would exactly stick to the same strategy, and the robot would not slow down as expected. And to fix this, we need players to explicitly reason about time-varying feedback strategies. So a feedback strategy is exactly what you expect. It's a strategy that we denote here by gamma, which maps the state and time to the player's control decision at that time step. So UTI is gamma I of x, t, and t. And the nice thing about a feedback strategy is that even if we fix a player's feedback strategy, that can still result in different states and inputs for that same player, depending on what the opponent does, right? So if this feedback strategy says, I will always keep a certain distance from the robot, I don't know, and have some PID controller tracking my goal, for example, then with a fixed strategy for the human, the robot can try out different trajectories, so to say, and reason about how the human's trajectory changes. So if the robot was to slow down, it would understand that the human will go slower and sort of not hurry so much. So if they care about minimizing the opponent's control effort, they would see some signal there, and they would then figure out, okay, if I go even slower, then the human isn't scared by me at all, and the human can save a lot of control effort, to stay with the previous example. Now, in order to find these feedback Nash equilibria, we'll have to go through quite some complicated computation. And so this slide, I'm building this up sort of incrementally, and it may be a bit scary, but as a disclaimer, you don't have to understand every little bit of detail. I just want to show you what technically you would have to do. The key idea is that we will have to find a strategy profile gamma star that is an equilibrium not only at the current time, but for all subgames. And we do that by solving the following optimization problem. We define the strategy of player I as something that returns U in the set of the arc minimizers, which is an optimization problem over only the ego player's input at that time step. But U is chosen to minimize the cost, in which the ego, so this cost is a function of the state, which I will show you how it evolves in a minute. Then it's a function of the ego player's input, which in turn is controlled by their strategy, and the opponent's strategy. So this opponent strategy here is kind of a fixed variable from the perspective of player I, right, in the optimization problem of player I. But what do I mean by this gamma tilde I? This is the strategy that's set up like this. This feedback strategy chooses at the current time our own control input UTI, which is exactly our decision variable. And at all future time steps, it re-invokes optimization. So this strategy is implicitly defined as the strategy that optimizes at the next time step from there on forward, which is a bit kind of, which directly already hints at some recursive structure here. And the dynamics in this game then are exactly dictated by these the closed loop dynamics that you get from following these feedback laws for each player, right? So here I'm just plugging into the dynamics, which are potentially nonlinear. The next state is the dynamics evaluated at the previous state, and the control inputs of each player is dictated by their strategies. And then finally, to also capture the generalized equilibrium concept, we'll also have some constraints for the teeth in control input of player I, which in general may be a function of the state and the opponent's inputs. And here I'm also encoding any sort of future state constraints directly in the input constraints, because you can reformulate them like that, right? Okay, so this is quite a hairy optimization problem. And this is also, I'm not expecting you to understand all of this. I mainly want to highlight that this is a really challenging nested equilibrium problem. So if you stare at this, at all the places where we've invoked gamma, we've effectively asked our optimization problem to evaluate another optimization problem nested inside of it, right? So we get a T, if T, capital T is the number of stages that we're modeling in our feedback game, then we end up with a T-stage nested equilibrium problem, which is completely intractable to solve online. So unless there's some very special structure to the cost and the dynamics, this is just very difficult. And if you're interested in the details of how this could be approached, I encourage you to go to Forrest Lane paper on the computation of generalized feedback Nash equilibria. But long story short is there is no free lunch, and we will have to make some approximations for this to become remotely tractable. Okay, and that is exactly what motivates the development of ILQ games, which is an algorithm for approximating feedback Nash equilibria. The key idea of feedback Nash, of ILQ games, is that when the dynamics in a game are linear and the costs are quadratic, we get a so-called LQ game. And for this LQ game, we have a closed form solution, which you can simply look up in Bashar's book on dynamic non-cooperative game theory. And we can use this closed form solution to also construct approximate solutions for non-LQ games, so games with nonlinear dynamics and non-quadratic costs, by iteratively approximating the feedback Nash solutions in a scheme that's very similar to iterative LQR. So let me walk you through this. We will start with some initial guess for the strategy profile. So we have an initial guess for the strategy of each player. And in the simplest case, this may just be one strategy. This may just be a strategy that applies no input. And then we proceed as follows. First, we roll out these strategies with the nonlinear dynamics to get the trajectory of the nonlinear system as governed or as induced by these current strategies. And then around this strategy, around this trajectory, we will linearize the dynamics via Taylor series expansion. So we get sort of a description of how the state evolves locally as a function of the deviation from the reference controls. And then we also quadraticize the cost. So we make a quadratic model of the player's costs at that stage, around that trajectory. And so with that, we now have an LQ game for which we can get the closed form solution via a coupled Riccati recursion. And the nice thing is that the controllers that pop out of this and turn out to be affine controllers. So the controller for player I is simply some linear feedback gain times the delta x plus some feed forward term, and they are time varying. And so this is very cheap to compute. And then finally, we will use this LQ solution as a step direction for our original strategies. So we will effectively step in the direction predicted by this LQ game solve. The details of that are a bit involved, but basically you can kind of treat this as a Newton step, more or less. And we will, in practice, apply some additional line search, which effectively makes sure that we're not choosing step sizes too large. So we're searching in the direction delta gamma for the best step size. And then with these updated strategies, we will again roll out the nonlinear dynamics and repeat. And we will repeat this until convergence, which means we will repeat this until the LQ game solve no longer updates the player strategies. So there's no longer innovation. Now, first, let me lead with some limitations. So first of all, we can only solve LQ games without constraints in closed form. So the simple version that I'm showing on the left does not handle constraints. There exist extensions, and those are exactly described in Forrest's paper on this topic, but then the algorithm gets much more complex. However, in many settings, we may not have constraints, or we may be able to write down the constraints as penalty functions for players. So this is not all that bad for many applications. And then the second limitation is that ILQ game solutions, they are not exact feedback Nash. They're not even exact local feedback Nash. And the TLDR, that's also explained more in detail in Forrest's paper, is that they ignore parts of the downstream strategy gradient. That sounds very scary, but the good news is that in practice, these ILQ game solutions, they capture the characteristics of feedback Nash solutions very well. It means that they capture these indirect feedback effects and all the other things that we've highlighted as limitations of open loop games before. So they're able to sort of improve on that, and you get good performance from them in practice. So there's some nice examples where people have compared them for like competitive decision making, and they also converge very fast. And that's basically due to the fact that we're taking simultaneous updates for all player strategies with this closed form solution. And perhaps the strongest aspect of this algorithm is that it's very flexible. It's very easy to extend this same idea to other equilibrium concepts and other information patterns, simply by changing this inner game solve to any other game solve for which we have a closed form solution. So for LQ games, we know the closed form solution for open loop games. We know the closed form solution for Stuckelberg games, both in feedback and in open loop, and Stuckelberg is something that I will not cover in this talk, but you may have heard it before. Basically, for LQ games, there's many closed form solutions that are well known. And simply by changing this atomic block in our algorithm, we can then use this result to also approximate the non-LQ solutions. And in some settings, for example, in open loop, this doesn't even induce any approximation error beyond sort of local Nash. Okay, so this is a very useful tool in practice, I would say. So that concludes the chapter on feedback games. And next, I would like to talk about settings where we have an incomplete game model, which is what the first question hinted at, and which will also turn out to be able to capture multimodal behavior. But before we go there, are there any questions?
Hi, hey, good presentation so far. So I wouldn't take too much of your time. So quick question on the scalability of the method that you just proposed, because usually that's the complaint with these things, right? Like you run into a problem because first example you showed of this massive intersection, and you have like 10-15 players actually interacting. So kind of question on that. And second question is more on the philosophical side of kind of juice being worth the squeeze question is like, have you had a chance to work with data sets in general and seeing, do humans in the real life follow Nash equilibrium when they're actually doing decision making? Like, have you had a chance to compare that with the humans' actual decision making in real world?
So yeah, let me process these questions in that order. So the first question was on scalability. And yes, my real-world decision-making problems, they often involve many more players than 5, which is roughly like So I guess I think the largest game that you can reasonably solve usually like maybe 7 players or something like that, depending on the task complexity. But clearly it's easy to think of tasks where there's more than 7 players. Philosophically, I would argue that if I'm interacting in traffic, I never pay attention to probably more than 3 players at the same time. And it's a matter of selecting the correct players to reason about in this very detailed view. And you can probably make simpler predictions of other players' decisions in a different way. There's some really nice work by Makram Shaheen from MIT on selecting players that you should care about in a quite principled way. And I do think that that's a very interesting research direction. But I don't have a better answer than you have to figure out whom to focus on. I'm very optimistic that there's a good game to solve that you can identify based on maybe even simple heuristics. There's some stuff from Michael Kokenfender's lab on like using decomposing games based on visibility and stuff, and they got some interesting results. So that's the first answer. And then the second question was on whether humans follow these games. So that's of course an important aspect. So there's first of all, there are some interesting results, also quite recent stuff, which I think I've seen in the reading list on like people using Nash equilibrium concepts inside transformer architectures for behavior prediction, and they show that this induced structure of the game indeed improves prediction performance. So that I think is at least a good hint that that this helps, and it's a good prior, or it's some good inductive bias in a sense. But then, of course, these games also assume that players are rational. And that's maybe a strong assumption to make. There's some very interesting extensions to, for example, noisily rational models where people look for sort of maximum entropy solutions. They are called entropic cost equilibria in the context of games. And in that setting, you can kind of also model suboptimal behavior and this kind of stuff. And yeah, that's certainly possible if you're sort of worried that in your application, humans are potentially doing very irrational things. Does that answer your question?
Yep. Thank you so much.
Nice. Okay. Nice. Then let's continue with the last chapter of this talk, which is on contingency games. This is joint work with Andrea and also Chiu-Yuan Chu and David, Forrest, Laura, and Javier. And the main idea of contingency games is to extend this decision-making framework to settings, to situations where we may not have a complete model of the game. And to motivate that, let me return to the example that you've seen earlier, but show you a larger frame of the same interaction. And you can see that this is quite an extreme situation where this pedestrian first decided to run to the left, and then in the middle of the road decided to go back, right? And so if we put ourselves in the situation of the driver, now that we've seen this interaction play out, if we were to drive along this road, we probably would see this player around this time. And so we've seen them coming from the right. So we will likely predict that their goal is somewhere on the left. They're also running in that direction quite quickly. So we may predict that they will continue in that direction and plan to pass them on the right. But as an experienced driver, we would probably know, okay, I don't really, this human has just done a very stupid thing. So maybe they just turn around any minute. And I'm aware that people sometimes do weird things. So I'm not 100% sure that they continue to the left. I'm also considering a possibility for them to go right. And therefore, I will potentially prepare to slow down in order to hedge for that outcome. And I would also be aware as a human that I will get more information about what exactly they want to do later in the interaction. And it's exactly these types of uncertainty and this reasoning about getting information later that we would also like to accommodate inside this game. And so to do that, let's revisit what our game model is missing. The key ingredient that we've already sort of had in the very first question in this lecture is that in practice, we may not know the exact intent of other players a priori, right? So that may manifest at not knowing their goal position. We should usually know what we want ourselves, so the robot should know their cost. Otherwise, the problem is specified, but for other players, we may not know that. And so, yeah, here, this would be manifested as we don't know the goal position of that player. And so we can treat these unknown aspects of the game as unknown parameters of the game. So we can make a parametric formulation of the game, and we can say, well, theta now includes all the things that I may not know. That may be the intent, and that's what we will focus on here, but that can also be stuff like the other player's dynamics or their initial state or other aspects that I'm uncertain about, right? And then I can maintain a belief over these uncertain parameters of the game, basically by looking at the past behavior and updating my posterior distribution over which parameters are likely under the observed behavior. And the TLDR is that there will be a nice talk on this by David Friedrich-Keil on inverse games, which includes some of this stuff in week 9 of this lecture series. But for now, just we will assume there is this belief which gives us a distribution over theta. And the goal is to accommodate this belief during planning. And that's exactly the thing that we try to tackle with contingency games. Yes, there's a question.
Oh, does this assume that there's kind of some like feature space of like the cost function, and like maybe you don't know, like say what the goal is, but you know that there is like a goal, like distance to goal feature of your cost function, and you just don't know the goal, maybe you don't know the weight. But if there was some other feature that you didn't even know that you should attend to, like you can't really capture that with this, or am I missing?
So yeah, the assumption is that you know the goal, the cost structure, but it's not necessarily that theta appears linearly in that structure, right? So it's not that just the weight, but it may also be the goal position or some dynamics that appears non-linearly in the some parameter that appears non-linearly in the dynamics. But yes, if there's something that you completely haven't foreseen, then this doesn't work, of course. My main answer to that would be, if you are worried that a human may do something very dangerous in the situation, just include one hypothesis that they are just solving a zero-sum game. So you can also have as an option in your belief that they may be your adversary. And that's actually something that you can also use to robustify your decision-making with this contingency game setup. But yeah, the whole idea, I should say, is that in these inverse games that David will discuss in week 9, you kind of want theta to have some interpretable meaning. Otherwise, you don't really get some interpretable inference, right? If you are just interested about some trajectory, you can just use your favorite trajectory predictor, and you will just have no explainability. But if you care about some structure and inducing the structure, then that's a price that you have to pay.
Thank you.
Okay, nice. So we'll assume we have this belief, and we now want to include this in planning. And so to start this discussion, we can first look at what can we already do with the tools that we've seen in the previous 2 chapters. Well, if we have this belief, say this it's just a categorical belief over 2 options, the human may go left or they may go right, then one simple thing that I can do is that I can ignore all but the most likely intent. So I will just assume, well, my belief is slightly higher for the hypothesis that they will go right. So I will just ignore that they may go left. So I make a map estimate here, and then I simply solve the fully observed game exactly under that point estimate. So I will just solve a certainty equivalent game. And so even though the belief knows that there's these 2 possibilities, one that the human goes left and one where they go right, during planning, we'll just ignore that alternative version of this interaction, and we just fully commit to passing the human on the left here. And of course, the benefit of that is that we can just use the solvers that we've seen earlier without any added complexity. But that's also potentially unsafe, right? So if the human decides to, if the human indeed wants to go left, then we are on a direct course with collision. And in the worst case, this may be the case for with 50% probability mass in our belief. So that's not a really safe way of making decisions. On the other end of the spectrum, people have also explored what here I'm calling fixed uncertainty games, in which a robot chooses a single trajectory tau r to minimize their expected cost under the distribution of possible human intents. And they are tasked to avoid collisions with all possible hypotheses for the human. So what happens here is that the robot plays against k copies of the human, 1 for each intent. And they have to find an ego trajectory that minimizes the expected cost under all of these opponent models, while avoiding collisions with all of them. And so if we think about our example here, because we have some non-zero probability mass for them to go left or right, and we don't want to pass them, want to pass behind the human, one safe thing to do is just to come to a full stop to certainly avoid a collision. So the nice thing is that this indeed accounts for uncertainty, and it indeed captures the entire belief without just sort of reducing it to a point. But then the problem is also because this doesn't model future information gains, so it doesn't model the fact that this belief will change in the future, this may be overly conservative. In this setting, we've just decided to come to a complete halt, and this may not be the best thing to do in this setting. And so the idea of contingency games is to bridge this gap by modeling, by accounting for uncertainty and modeling this entire distribution, but accounting for the fact that we will get more information in the future, but we want to capture this sort of information gain in a tractable way. And the high-level idea, returning to our video here, is that what we will do in contingency games is that we will plan with the current uncertainty in our belief, but we will anticipate certainty in the near future at a future time we call TB, the so-called branching time. So we have this kind of simplified model that we will have uncertainty until TB, and after TB, we will be fully certain about the intent. So in our abstracted version of the problem, this means that before TB, the robot will develop a single plan that must work for all hypotheses, and it must trade off the cost under the different hypotheses according to the likelihood, but must be feasible under all of them. And then after TB, the robot has separate plans conditioned on each outcome. So effectively, this contingency game gives you a multimodal prediction for the human and a conditional plan for the robot. And mathematically, we will achieve that by a framework that's somewhat similar to the fixed uncertainty setting. So here, the robot will minimize their own expected cost under the distribution of important intents in the belief. But importantly, we endow the robot with k copies of the trajectory. They have k different plans, one for each hypothesis. So here we have two hypotheses. And so if the human goes left, we will pass them on the right. And if the human goes right, we would pass them on the left. And then also each of the hypotheses sees their corresponding constraints under that hypothesis. So in each case, we have to avoid collisions. But importantly, since the robot cannot know which of these hypotheses is true before TB, we constrain all of these K plans to be consistent up to the branching time TB. So we need an actionable plan until TB, right? And therefore, we constrain all of the plans to be identical up to that time point. And so in order for this to be coupled or closely coupled with the human, this conditional plan of the robot plays against k copies of the human, one for each intent, as in the fixed uncertainty game. And so, we have these sort of k ghost versions of the human, each of which act under a different intent, and they only see the robot. They don't see sort of the other copies of themselves, but the robot has to play against all of them simultaneously with this conditional plan that they compute. And so in the setting, then, the human part of the solution is a multimodal prediction that is now coming out of this game. And the robot's part of the solution is a corresponding conditional best response plan. And for us to build some intuition about the dynamics of the solver, we've built a little web widget that you can also see on the website that I will show on the last slide. And we can vary the different parameters of the game solver to build, to get a better understanding of how it works. So first of all, we can see that if we vary the belief, the robot will balance the cost of the different hypotheses according to their likelihood. So for example, if we think that it's very likely that the human will go left, then we plan to pass them on the right. And so we are kind of accepting that, well, even if that's not true, then we are happy with scaring the human a little bit, and they will just have to jump out of the way, right? So we are planning, we think that at this time we will figure out what the human wants to do. And so because we've developed this conditional plan, then even last minute we can still turn around to remain feasible. And so if the true human's intent was the opposite, so if our belief of them going left was correct, then we can actually quite smoothly proceed to our goal. Okay. And similarly, we can also vary the branching time, which is the time at which we assume certainty. And we can observe that if we choose low branching times, or early branching times rather, then we get more sort of optimistic plans that assume that uncertainty will resolve quickly. And if we have high branching times or late branching, then we get more conservative plans. And at the extreme ends, we get this previously discussed game-theoretic methods as a special case. At the lower end of the branching time, we exactly get the certainty equivalent game, where now we've just computed the solutions for each outcome, right? And we would have to commit, because there's not a unique control input, we now have to maybe, for example, commit to the most likely one. And at the upper end of the extreme, we have a fixed uncertainty solution where we assume uncertainty will never resolve. And so we just have a single plan for the entire trajectory, for the entire horizon. Okay. So to summarize what I've shown in this demo, the key message here is that that contingency games include these other two paradigms as a special case, with certainty equivalent planning at the one extreme and fixed uncertainty planning at the other extreme. Okay, and so to summarize, right. So that's of course only the generation of the plan at a fixed time step. At runtime, we will again wrap this in a receding horizon replanning loop in this MPGP framework, where now we will update the belief and the branching time online at every time step. And if we do that, then we get some very nice behavior, and we get this adaptive game-theoretic motion planner that reacts to the uncertainty in their belief, and they will anticipate the future time at which uncertainty will resolve, and sort of trade off safety and efficiency. And we've done some extensive evaluations of this planning mechanism against game planners from both ends of the spectrum, both certainty equivalent games and fixed uncertainty games. And the key result is that this contingency game generates more efficient plans that are more efficient than fixed uncertainty games, but reach a similar level of safety. So they also outperform certainty equivalent games in terms of the safety aspect. And so if you want to read more about this, also if you want to play around with this widget, you can visit the project website at the link below. Okay, so that concludes sort of the last chapter of this talk. I would like to now summarize the main takeaways of this lecture from all the 3 chapters. Overall, we've seen that dynamic games capture interaction quite well, and they capture them via coupled optimization. So we've seen how we can formulate an interaction as a coupled optimization problem. In the open loop setting, we can solve these games as a mixed complementarity problem by rewriting them, writing out their KKT conditions and then rewriting them as an MCP. We've seen that if we go beyond open loop information structures to feedback games, then these problems become quite difficult to solve exactly. And the main takeaway there is that these feedback games have desirable properties, but they're kind of intractable for online decision making. And so a good approximation for these problems are ILQ games, which we can use to tractably approximate feedback game solutions by iteratively applying the closed form solutions of linear quadratic games. And the nice thing about this algorithm is that it readily extends to other equilibrium concepts like open loop Nash, but also Stackelberg. And finally, we've also seen how we can deal with situations where we have incomplete knowledge of the game model, for example, incomplete knowledge of the costs of other players, and we have a belief over these quantities by using contingency games to compute conditional plans for the robot. So yeah, this concludes the talk. If you are interested in using any of these things, either in a class project or in your own research, we've created a GitHub organization where we started to publish some of these solvers, which is the Julia Game-Theoretic Planning GitHub organization. And there's also a bunch of stuff on my own GitHub, which I will slowly move over to that organization. The software tools there include tools for modeling games, rewriting a given game So you write down the game in terms of dynamics and costs, and it automatically generates the MCP solver for it, so that you can solve it online. We also have tools for differentiating game solutions, and we have an IRQ game solver. So if you want to work with something like this, don't write everything from scratch. There's some code out there that you can use as at least as a starting point. Okay, that concludes my talk. Are there any questions?
Thank you, Lasse.